Okay, so good morning, everyone. I'm Kijin Song, and I'm a postdoc researcher in the Urban Information Lab in the School of Architecture at UT Austin. Welcome to our lightning talk series on smart city research. And this talk series is funded through the UT's Good System project. So we invite speakers from academia, industry, and the communities to share the research interests and the research events and the needs related to the smart cities. So if you are interested in this topic, please feel free to visit our website for our past talk and other activities at smartcity.tech.utexas.edu. And for today, we are very excited to have Dr. Chao as our first guest speakers for this fall. Dr. Fan is an assistant professor of civil and environmental engineering and earth science at Clemson University. He received the PhD degree in civil engineering from Texas A&M University in 2020 and the master's degree from UC Davis in 2017. He has authored 30 papers in peer-reviewed journals such as Royal Society, Computer-Aided Civil and Infrastructure Engineering, International Journals of Information Management, Scientific Report, and IEEE transactions, including two ESI highly cited papers. His work has appeared on more than 20 international news media, such as ASCE, Civil Engineering magazines, and Bees.org. He serves as a reviewer on 37 peer-reviewed journals and a member of a program committee for 11 conferences. His talk for today is titled that Digital Twin of Urban Systems Towards Intelligent, Climate Adaptive, and Equitable Cities. So without further ado, I'll pass the mic to Dr. Fan.
Right, thank you. Thank you so much for having me here. So I'm so glad to share my research. I'm Chao Fan, the assistant professor at Clemson University. So I'm a brand new assistant professor and just want to share some of our recent work related to the digital twin of urban systems towards intelligent, climate adaptive, and equitable cities. Okay, so so as we can see that our globe are experiencing or suffering from severe disaster impacts, which is increasing and also disproportional. So we can see that from the past few decades, the number of deaths due to the impact of disasters increases, and also we lost a lot of infrastructure and humans during the disasters. Also, we see that the impact of disasters are disproportional to different income populations. For example, the low income, lower median income populations suffer from the disasters more than the high income populations. So how can we deal with these challenges of our globe? How can we mitigate the impact of disasters in the future? So our urban systems are very complicated. So they have complex interactions between different urban systems, between the environment and the and the infrastructure. So when we look at the urban systems, it's almost as the nexus of human disaster and the building environment. So our urban systems require more intelligence to deal with the challenges brought by the changing climate and the disasters. So this promotes or motivates the idea of digital twin of urban systems. What is digital twin? Digital twin is a digital replicate of a real world urban systems. This can help us to pairing the digital and the physical world, and also it is data enriched who can provide the monitoring of the environment, the urban systems, and also the activities of our populations. Also, the digital twin can incorporate some models and methods by using AI. So we can call the AI-enabled simulations to head off problems before they occur. So this helps the urban systems to prevent the downtime and also trying to save the lives of the populations due to the disruptions of the infrastructure and the urban systems. So with all of these capabilities, what specific activities or what specific steps we should have taken on based on the idea of digital twin. So when we think about the real world systems, we see that the communities are operating because of the interactions between human infrastructure and the environment. When disaster happens, for example, the flooding may flood the infrastructure, may flood the road, and also we will generate some situational information related to the population activities in face of the disasters, and also the impact of disasters on the buildings and on the roads, and also on our telecommunications. So all of this, the evolving situation will generate a lot of interesting and important data for us. The data layer, including like the mobile phone location data related to the activities of the humans, environmental sensors related to the how the environment is being changed, right? Also, we can have the data related to the communications of the populations regarding the real-time situations. Having this data, what we do next is trying to analyze the data to extract the knowledge and solutions to inform our decisions for disaster mitigation or disaster adaptations, right? So here we have a lot of approaches that we can adopt from the domain of AI, like the representation learning over the graphs for nonlinearity capture. Also, we can adopt the differential equations to capture the dynamics of the urban systems. Using this model and by applying this model to the data sets, we will have the chance to generate a human interpretable knowledge and information to identify the geometric patterns of the disaster events. Also, we can capture or model the dynamical mechanisms of the disasters. Trying to use these models and knowledges generated from the data set and also the models to help us to make some predictions or extract some insights related to the behaviors of the urban systems. This can be integrated into the digital twin of the urban systems to help us to make the decisions for the climate adaptations. So in this presentation, we just want to talk about some of the research we have done towards the vision of digital twin and how we can incorporate this into digital twin to help us to build the intelligent, climate adaptive, and equitable cities. So the left part of this research is related to the real-time disaster resilience. We are trying to see what technologies we developed to build the community resilience during disasters. And also on the right-hand side, we trying to develop models and trying to optimize the urban systems in order to improve the adaptation of the urban systems during the changing climate. Okay, so the first work I would just want to talk about is the real-time sensing. Especially during disasters, we know that many people post a lot of information on social media to trying to show their real-time situations during disasters, also help the other peoples to survive from the disasters by knowing their real-time situation. So a lot of information has been posted on Twitter, but the challenge is that how we can leverage all of these informations to inform the decision-making, to inform the first responders, to make the resources allocation and search and rescues, right? So what we want to do here is trying to process all this massive data posted on Twitter and to extract the valuable informations that allow us to identify the severe impacts of the disasters in near real time. So what we do here is trying to extract the tweets and convert all the tweets into a vector so that the computers can read these tweets using these vector representations. So this we call trying to transfer the tweets into the computational models. And then using that, we can trying to calculate the distances between different tweets. So some tweets may deliver similar information. Using the vector representation, we can measure how close these tweets are delivered the similar information, right? Also, if the tweets are distinguished from each other, they are totally different, then we also identify them by measuring the differences, the distances between the two vectors representations. So having this kind of representation and calculations, we build the semantic network where the nodes are representing the tweets and also the links representing the similarities between the tweets. So the tweets having more critical or comprehensive information related to the specific infrastructure disruptions or some disaster events, they can be identified as the critical tweets, which has the highest connections or involved in the highest density dense subnetworks in these networks. So we're using the network matrix called a weighted degree, trying to identify the tweets that can deliver the most valuable, comprehensive, and validated information from the semantic network. The information extracted from these critical tweets are considered as the important information, situational information to inform the decision making in disasters. So here we show some results related to by applying our research, our methodologies to the Hurricane Harvey events. So we find the situational evolution in the mainland neighborhood in Houston. We can see how the flooded emerge on the street and how the extent of flooding in the neighborhood and what human actions has been taken and when the waters have been receded, right? Also at the end, what damages we found from the neighborhood. So all of this information are extracted from the tweets, and all these are critical information which can help us to identify the real-time situation and inform the disaster response. The second study we want to talk about is how we can make the predictions about the future. So during disasters, we are not going just to know the real time or current situation. We also want to think ahead to learn about the situation in the future so we can make some proactive actions to protect ourselves and our properties. So especially what we want to see is how the flooding would propagate from through the road networks, right? So this will be important to some tasks like evacuation or disaster relief, search and rescue, etc. So the question we ask here is how many roads will fail to service next? Where will the road failures be, right? So first we identify the number of roads that will be flooded in the next couple of hours. And also we want to see where these flooded road segments are, right? So to address these challenges, we created the network population-based contingent model. Here we consider each road have four status, like a functional flow. That means people, the cars or vehicles can pass through this road easily. Flood incubation, that there means the roads has some flood waters. Flooded means that the roads cannot be passed because of the flood waters. And finally, the road may be recovered because of the receding of the flood waters from the road networks. So we're trying to capture the entire process of the flood propagate and recede from the road networks. We build a differential equation model trying to capture the propagation processes. So when some roads are flooded, what will be the next flooded road segments, how many road segments will be flooded next, right? And in the receiving process, we want to see when the road segments will be recovered and how many road segments will be recovered in the next time period. Okay, so we formalize this problem as in like optimization problem. So we trying to feed the model with the real-time data and to find the parameters related to the incubation rate, the propagation rate, and the recovery rate. Okay. Then by applying this model to the Hurricane Harvey events in Houston, we can see that the models can capture the entire process of the flooding over the road networks. We can predict not only the number of road segments in near real time, and also we can identify the locations of the flooded road segments. You see, we apply the model in different time windows. As for 4 hours means we collect the data in every 4 hours and trying to feed the models and make the predictions in the next 4 hours to see what the situation would happen in next 4 hours. Also, we look at the situation in 8 hours, 12 hours to see if the models is adaptable or if the model is applicable to the predictions in the in longer time, right? Like 8 hours and 12 hours. So from the results to identify the specific locations of the flooded roads, we see that in 4 hours the precision is quite high. But in all of these three models, we see that at the beginning, the model may not perform very well because the model is not able to identify the initial flooding area. This is kind of the limitation of the model. But as long as we find the initial flooding area and also gather sufficient information, we are able to make accurate prediction about the flooded road, number of flooded roads, and also the location of the flooded roads in the next few hours. The next study, we just want to talk about how we trying to optimize the urban systems to make the cities climate adaptive during regular times. The most important issue that we think about is the equality. So especially the cities are more unequal to for the people to be adaptive to the climate. So how we can measure the inequality is the first task we tackle to the climate adaptation challenges. So especially when we look at this picture on the left-hand side, we see that even for a very small grade of the cities, it has a lot of features or a lot of attributes that we want to take a look at. For example, we have a variety of facilities in this small area of the cities. We have a lot of human life activities like going to grocery stores, going to pharmacies, going to restaurants, etc. So they have a lot of activities performed at different times, right? So also they have the network topologies based on the physical locations of these areas. It can be located to other small grids, physically adjacent to other places, right? Also, they have some demographic information to see how many residents are living in these areas, right? So all of these features are all included in these urban areas. So this creates the challenge to measure the inequality for the entire cities. How can we incorporate all of these attributes and the network topologies into the measurement of inequality? So conventional statistics may not be able to achieve very promising group similarity measurement or network topologies. So we really need a method that can allow us to incorporate all this information in the measurement of inequality. What we do here is we use the neural network models, which can allow us to construct a feature matrix and also adjacency matrix. Adjacency matrix include all the information related to the network topologies, especially the physical or spatial network topologies of the cities. And the feature matrix, we trying to include as many as possible of the features related to specific areas like the demographic features, human activity features, and also the built environment features, right? All taking this as an input into the graph convolutional layer, which is the embedding models, we can generate the embeddings for specific areas in the cities. So each small grid can be represented by one representation vectors. So this is a kind of the idea to make the computers or optimization models readable about the cities. Okay, so having this model and having these embeddings, what we do next is trying to make some predictions about the social economic labels of these areas, trying to see if these areas are occupied by high income white, low income white, high income black, low income black, etc. So this model is kind of a measurement of inequality. If this machine learning model can accurately predict the social economic labels of these areas, that means those features, urban features, can distinguish different areas. That means the areas are very unequal. But if the machine learning model or the metrics of the model is quite low, that means the machine learning model cannot distinguish different areas based on the urban features. That means the urban areas is very equal, right? Because the urban features cannot distinguish different areas, right? So this is help us to do the measurement of these urban areas. Then we can know that if the city has a very high F1 score, have a very low F1 score, that means if the city is very unequal, or if the city is very equal, right? So having this knowledge in mind, or having these quantitative metrics, what we do is to see what's the relationship between the inequality of the cities and also the kind of spatial distribution or the attributes of the cities. What we see here is we find the correlation between the facility distribution and the F1 score, which is the inequality measurement. We see that as the S1 score increase, the facility distribution centrality index also increase. That means the distribution of the facilities is highly associated with the inequality of the cities. Also, when we look at the road network of the cities, we also find that the cities have more dense road networks, tended to have a lower F1 score. That means the cities have more roads in the cities would be more equal, right? So this kind of knowledge help us to see what we can do to help cities to be more equal. So the next step is trying to see what we can do to improve the equality of the cities, and furthermore, how this would impact the resilience. Okay, so having this knowledge in mind, we want to see how we can optimize the facility distribution and the road networks in the cities in order to improve the equality of the cities and further look at the interactions between equality and resilience. What we do here is we build the optimization model to try to characterize the needs of the residents and also their access to the facilities. So we have a bi-party networks. On the left-hand side is residential and residential populations and areas, and the right-hand side is the facilities. And we use the needs identified from the mobile phone data of the population activities to measure the needs of the residential area to specific facilities. And also we measure the distance between the residential area and the facilities using the OpenStreetMap, using the road networks. So here we're trying to optimize these equations by considering the travel cost, which is the travel distance we considered in this model, population needs, and the population size in these residential areas. By minimizing that, we can able to obtain an optimized solutions for the distribution of the facilities in the cities. Then we want to think about what's the impact of improved equality of population access to resilience. When disaster happens, what would happen to the urban systems when it is optimized based on our models? So we're trying to build the dynamics models based on the satisfied demand of the population to specific facilities, and also the unsatisfied demand of the population to the facilities during disasters. So we want to see if we change the facility management, what would be the change to the satisfied demand in these dynamic models to measure the resilience of these optimized urban systems. So we find that equal access is associated with improved resilience. So when we improve the metrics of the facility through the optimization model, then we see that the resilience is also improved compared to the empirical distribution of the urban systems. So this is what we observed from the models and also our findings. So finally, I want to summarize that the data and the AI approaches can enable the digital twin of the urban systems and further to help the cities to survive from the changing climate. At the end, I would like to use this flyer or kind of recruiting information to conclude my presentation. I'm a new assistant professor at Clemson University. I'm looking for postdocs, PhD students, master students, undergraduate research assistant to join our research groups to do interesting and high impact research. Also, we welcome to any academic and industrial collaborations with our lab. Feel free to reach out. Yeah, thank you so much.
Thank you so much, Dr. Fan. I think that's a very interesting talk. I'll just wait to see if there is any questions from audience. But one question I want to throw out first is, I know there are lots of the social media researchers and using the tweets, and I thought that some data from the social media that collects some people's sentiments, like using some sentimental analysis, it's much more subjective and much more easier to collect. I mean, rather than the collecting some more objective information, because I think objective information like flooding events or some more information like the disasters, that should be verified like more disinformation, and if there is some reliability issues on the information. So I think because you have collected some flood information from the Twitter data, so I would like to ask, have you faced those issues when you're collecting the data, and how did you deal with those issues in your previous work, and do you have any thoughts on that?
Yeah, thank you for the question. Yeah, this is a very important question, especially when we talk about the Twitter data or some social media data from different platforms. We always should think about the question related to population bias or the information reliability, right? So not all the people using the social media, not all the information are correct or reliable on social media. So especially when we develop the methods, we should think about these problems. The benefit or the kind of advantage or the kind of merits of our method is that we trying to avoid these biases by construct a new research question. So what we want to do in our research is just trying to gather the reliable real-time situational information related to the building environment and the disasters. So we avoid the population biases in our data in the approach, because what we generated from this our approach using the social media data is just the objective information, right? It's just the information related to the infrastructure system, related to the disasters. So if there something are not posted on the social media, but exactly happened in the building environment, we are not able to collect. This is not the reason of the method. It's not the kind of disadvantage of the method. It's because of the data set. So we don't want our result to serve as the individual or the single data sources or the information sources for decision making. We just want to provide a contemporary or kind of supporting information to the decision makers, that if they cannot collect the information from other sources, we can still use these social media sources to learn more about the situation. I don't think any information channels can be super comprehensive. So we need to incorporate different information channels together to inform the decision making. And so our approach just to provide one channel of the information to inform, to help the responders to learn about the situation.
Thank you for your answer. Hui-Hai and Caitlin, do you have any questions?
I do have a quick question if there's still time.
Sure, yeah.
So I think in one of the slides, there was like a graph of how the model became more accurate at around day 4. So I was wondering what the scale of time was for I guess providing the information to implement disaster response, because things happen so quickly. So is it I guess what would happen on day 1 period if people are experiencing floods and can get swept away in a matter of seconds as opposed to days?
Yeah, so I think the time scale really matters, especially when we want to make the predictions in a future 2 hours or 4 hours. The model would be more accurate, because even the disasters not evolve so fast as 2 hours or 4 hours. But if we want to make the prediction about the next day or a few days later, it's really hard for the model to capture the behaviors of the environment or the systems, because there are a lot of uncertainties or factors that we should consider, right? So yeah, we hope in the future we can incorporate more physical processes of the flooding events, or some other factors that we can take into account, including the rainfall intensity or other factors related to the weather, right? Then in the future we can improve the accuracy of models, so that in the future, if we want to predict the situation in next few days, the model can still perform well. Yeah, this is a challenge. So we want to kind of devote our effort to address it in the future. Yeah. Thank you.
Thank you.
Hi, Dr. Fan.
Hello.
Can you hear me? Yeah.
Yes.
Thank you so much for your presentation. And I have a question about the flood prediction. So I think maybe real-time flood status data is necessary for your research. So my question is, how did you get that data, or what kind of sensor are you using to get that?
Yeah. Thank you for the question. This is a really good question. So yes, the data is really important for the models to perform in real time. So what we gather the data here is we use the traffic data over the road. So, you know, there are a lot of apps, people using apps to travel from one place to another. So the apps, especially the mobile apps, can identify the speed of the travelers from one place to another, right, all over the road segments. So when the road segments do not have any speed data, then we consider these road segments are flooded, and because no vehicles can pass through these road segments. So this is the data we collect to measure the flood events, but or the extent of flooding on the road segments, right? Also, there are many other data sources like satellite images, but it takes time because usually cloud may block the satellite to collect the images, right? Also, drones can be usable, but yeah, so but it still needs some techniques to allow the drone to collect the data in the heavy rainfall or strong wind, right? So yeah, there are a lot of sources, but what we use in my research is the traffic data on the road network.
Thank you.
Thank you.
Can I ask one more question, Dr.
Sure,
Fan?
yeah.
Yeah, so my question is, I think one of the big challenges in digital twin is to build some 3D replication of the physical works, which means how to replicate the physical world in 3D dimensional aspects. So do you have any future research plan to develop the 3D simulation digital twin, or what would be your future research direction based on your previous findings?
Yeah, thank you for the question. This is kind of a very interesting topic. There are a lot of researchers have been working on the 3D modeling of the cities, like the buildings, infrastructure, road, right? So a lot of work have been done related to 3D modeling, but I think the challenge or the problem that we still want to look into is how we can look at the interactions of the 3D models and the humans and the environment. So we should incorporate the activities of humans to interact with these 3D models so that we can have more insights related to the impact of the human activities on the environment, and also how human activities can inform the like design of the buildings or design of the infrastructure, right? So yes, in the future, we definitely want to look at the 3D modeling of the cities, but not just the 3D modeling of the infrastructure. We should also think about the incorporation of the humans and the environment in these 3D models. Yeah.
Thank you for your answer. Yeah, cool. It's very interesting. So we are already at the time to wrap up. So I want to stop here. And if you have more questions, please feel free to reach out to Dr. Fan directly. You can see his email here. And if you miss it, then you'll feel free to send us an email like we can. We're happy to connect you with Dr. Fan as well. So thank you so much, Dr. Fan, for your wonderful talk. And we'll post the videos on our website soon. And also thank you everyone for joining the talk, and have a great weekend.
Thank
Bye.
you. Thank you, Kenji. Bye.
Bye.